All right, so I'm going to go back and do another exponential growth problem. And then we'll take a look at some homework problems. In particular, we want to review that logistic one, which is pretty crazy. All right, so exponential growth. The formulas for exponential growth, there's variations on them, but the most basic one looks like this. Y equals some number, A, times some base B to the power X. And we can have different tweaked versions of that. So that's the basic one. So A would be our starting value. For example, suppose we go back to some bacteria and we started with maybe A equals 100 at the beginning. And let's let B equals 2. And maybe X is hours. So that right there would mean the population doubles every hour, right? Because I'm multiplying by 2 each time. So double every hour. Oops, wrong order. Besides being called the base, does anybody remember another name for that B? There's a phrase, actually. Madeline, you know this, we just talked about it. The growth, not growth rate, not ratio, starts with an M. The growth multiplier, right? We have a growth rate and we have a growth multiplier. So the B here is what's called the growth multiplier. And the multiplier, oh, you can't see my screen, I bet. I hate it when that happens.
Right.
Okay, sorry. Share screen. Oh, that's better. All right.
Okay, great. Thank you.
Yeah, the growth multiplier is always 1 plus, excuse me, the growth rates. So if I have 2 as the multiplier, what would the rate be here? No. The multiplier is 2, so 1 plus something gave me 2. What would the rate be? The rate would be 1, which is 100%. So that means the bacteria is increasing by 100%. Every one bacteria makes a new one, right? That gives me a doubling. Make sense? Okay. So, but rates are different than the multiplier. To get the multiplier, we have to add 100%. 100% is where we started with, right? So this number right here is my 100%, my base. Where did I start? So we're going to look at an application of this in finance called compound interest. Usually when you're playing, and compound interest is just repeated simple interest. So it's not as bad as it sounds. So note, there we go. It's just repeated simple interest. All right, so then we have to remind ourselves, simple interest sounds simple, but what is it? So simple interest is calculated by taking whatever balance you have multiplying by the rate, and multiplying by whatever time has elapsed. That's simple interest. Whatever your balance is, times the rate, times the time. Rates are usually given as annual percentage rates when we're talking about finance, not always, but usual. Abbreviated APR. So let's just suppose somebody gave us an awesome deal of 12% for an investment. Good luck finding that. I think only hedge fund managers get that. Rest of us get like 0.5%. And then for time, now since I'm talking about an annual, oops, that should have two N's, an annual rate, that means time has to be measured in years. So let's say 1 month went by. Again, the rate was given as a yearly rate, so I have to consider 1 month to be 1/12 of a year. So the time of the rate has to match in how you count time in the problem. And let's suppose our balance is $1,000. So to calculate simple interest on this, I would just take 1,000 times 12% times 1/12 of a year. And that's how much interest I would earn in a month, given this starting rate there. So it's new screen. So for me, my interest would be $1,000 times 12% as a decimal times 1/12 of a year. And everyone's whipping out their calculators, right? Help me out. $10? Yeah, okay. So that means I would get in 1 month $10 interest. Now, sometimes interest is paid in dividends. So a dividend means you invested some money with somebody and then periodically they will give you money because of the money they have. So maybe I invested in a company that's about to make a new cell phone app and they say, hey, every month we'll pay you like this for the $1,000 startup money you gave us. So that means every month I should expect to get $10 from them. That's called a dividend. However, what if I decided to reinvest that $10? That means my new balance would be $1,010. And then another month goes by, and I can calculate how much I'm going to get. Now we can clean this up a little bit. For example, what's 1/12 of 12%? What's 1/12 of 12? Yeah, be 1, so that means it'd be 1%. So the percent I'm getting monthly would be 1%, which would be that as a decimal. So does that make sense? If there's 12% over a year, it doesn't seem fair that I only get 1% per month. Doesn't that sound fair? Yeah, so that's simple interest is just a fair way to divvy out interest over a shorter or longer time period than what the rate called for. And a rate is usually a time-sensitive idea. So basically, to get my new interest here, I'm just going to take my balance, $1,010, multiply by my monthly rate, 1%. You could say over 1 month. That's kind of redundant, but we could say it. All right, what's 1% of 1,010? $10.10, right? Because 1% is 1 out of 100. Shift the decimal point twice. So I picked these numbers so I could do them in my head, by the way. 1%, 1 out of 100, shift the decimal point. I don't have to do anything fancy. We'll do some harder numbers later. Okay, so $10. So by reinvesting that money, doesn't it make sense that I should get a little more interest because I had more for them to pay me off with? Okay, so the idea of repeating simple interest by putting the interest back in the account, that's what's called compound interest. Your interest gets to collect interest over time. So that's like the way a savings account works. Savings account, they don't pay you each month whatever percent, they put it back in your account. So now your account's a little bigger than it was before. So the next month when you get interest, you get a little bit more than you got before. Now, unfortunately, savings accounts these days tend to be about 0.5%. So over a month, you would get 1/12 of 0.5%. And so if you're investing $1,000, let's just double check. What would that be? Let's suppose the bank had an APR of 0.5%. Let's see, what's 1/2 as a decimal? 0.5? 0.5%. Percent means shift the decimal another 2 places, so that means it's 0.005 as a decimal. Okay, so that's 0.5% as a decimal. Now, if I invested $1,000 at 0.5%, 0.005, but only for 1 month, now I get 1/12 of that. That I can't do in my head. If you guys could whip out your calculators. 0.416, so maybe 42. So you would get 42 cents on your $1,000 investment. At least you got something, right? I think banks give out lollipops now instead for every $1,000 you invest. Right? That's about a cost of a big lollipop, isn't it? 42 cents a month. So you can get 1 lollipop per month with the interest you get on 0.5% in a month. But you know, that 42 cents goes back in and it will collect interest, which will give me a little bit more money. Let's just see what would happen. So suppose we invested 1,042 cents at 0.5% for 1 month. Whip that on your calculator. So it's still about 42 cents, yeah. So our interest isn't collecting interest yet, it's too little. But eventually it would start to, like if we put $1 million in, now if we invested $1 million, they would certainly give us more than 0.5%, right? Because we'd be at a different bank than we're at now. We'd be at Donald Trump's bank, for example, whatever that is. But it takes money to make money, they say, and with interest, that is certainly true. So we're going to keep extending this idea and develop a pattern out of it. So we're gonna whip out a spreadsheet on the board here, then we'll try it on the computer, and we'll see what happens. So let's see. Let's do it again. So let's go back to a balance of $1,000, and we're going to bump up the interest rate again back to 12%. Because 12% is way easier to deal with. And we are going to collect interest monthly. So oftentimes in problems like this, they introduce a letter called N, and N is called the compoundings per year. Okay. So with the 12%, that's an APR, right? Generally, given rates are APRs, annual percentage rates. I'm also collecting interest monthly. So I just want to make a table to see what happens over a bunch of months. So I've got some time, let's call it 0, where I throw down $1,000 to some institution. 1 month later, they're going to calculate some interest, right? What are they going to do? Well, they're going to take my $1,000. They're going to multiply it by the 12%. Oops, which is going to be 0.12. and they're going to divide by 12 or multiply by 1/12, however you like. That is my interest, right? But if this is a savings account, doesn't my $1,000 still live at the bank? Yeah, so I will have the interest plus what I started with. And we already did this calculation earlier. That was one of the first ones we did. We found that this came out to $1,010. Right, because isn't my interest up here the 10 bucks? So after 1 month, I would have $1,010 in my account. Questions on that? Okay, so another month goes by. I'm in month 2 now. I had $1,010 in the month, and they owe me interest on that. How do I calculate the interest? Well, same way I did before. I take my $1,010 this time, which is my previous amount, times my rate, divided into 12 months. So I think that ends up an extra $10.10. So whip out your calculators and please double check this. If my arithmetic's okay, I think I will have $1,020.10. But I need someone to confirm that. This is now stretching my arithmetic skills. I got it right? Okay. All right, now I'm kind of doing the same thing each month. Each month I have a previous amount that's in the bank, and each month I have to calculate the interest on that previous amount. And don't I do it the same way each time? All that's changing is how much I had the previous month. So I think I have a recursive formula here. So we'll come back to the table in a minute. I'm going to skip over to a new page, and I think what's going on here is I'm taking my previous balance and I'm adding to it the previous balance times that 12% divided by 12, which is really 1%, 0.01. Can I clean this sucker up algebraically? I have 1 B and I have 100th of a B. How many B's do I have altogether? 1 100th B's, yeah. I now have 1 and 100th B's, right? Because that's 1 B right there. So altogether, that's 1 and 100th B. What is my rate of increase here? Isn't it 1%? Aren't I getting increasing by 1% per month? How do I turn a growth rate into a growth multiplier? +1. Didn't we just add 1 to our rate? Yeah. So this compound interest is a growth problem like we were looking at in this chapter. Okay. Now, usually they write the balance out front when they're doing the calculation, and they multiply by 1.01. And then the key there is the next thing to finish our model is we have some exponent up here. Okay. And let's see, how often do I collect interest in this problem? Once a month, right? So my exponent here would be just however many months have gone by. So this formula, I started with it right here. That's called a recursive formula, remember? Where we just keep repeating that pattern each time. Spreadsheet does a great job of that. Now that I've got it down to this formula over here, this is now what we call an explicit formula. Because all you have to do is say, hey, I kept my money in the bank for 2 years. I say, oh, that's 24 months. So if I raise that to the 24th power, that should be how much money I end up with after 24 months. I just keep repeating this. Let's go back to our table and check to see if this is true. So on my table, I now have 2 methods to calculate what's happening in the 3rd month. We can use blue. So in the 3rd month, one way to calculate it would be to say I have 1020.10 plus, repeat that, 1020.10 10 times the 0.12 over 12. My claim is that I can also take my original amount, 1,000, and multiply by 1.01 to the third power, because I've gone 3 months out. So let's do both of those calculations and make sure they come out with the same number before we move on. And that's the third power down there. It's a little bit messy. Try it again. That's a little better. Let's see. So I'm checking on another screen with my Google calculator. First calculation gives me $1,030, 30 and 1/10 of a cent. Okay, a little weird having a 1/10 of a cent, but hey. And then if I repeat that calculation, if I take the 1,000 times, oops, that's not a times, 1.01 raised to the third power, I get the same number. Okay, so hopefully they worked for you when you tried your calculator. I'll slow down a little bit here. All right, so I'm going to whip out a spreadsheet now. Let's see, growth models, new sheets. Call this compound interest. Do I have, what do I have? I have months, and I have money, and at first I have 1,000, and then after 1 month I have 1,000 plus 1,000 times 0.12 over 12. And since I'm just referring back to my previous amount here with cell references, let's blow that up a touch. Right, I should be able to fill that down. So I'm going to try. Oh, that worked. Yeah, it looks like it's working. So that's one way to do it. So I could fill it down for a whole bunch of months, like 24 of them, see what happens in 2 years. So according to the recursive formula on the spreadsheet, I'll have earned in 2 years almost $270 in interest. Let's compare that to the other formula. The other formula said take the starting amount, 1,000, multiply by the growth multiplier. What's the growth multiplier for 1%? 1.01, yeah. And then raise it to the power however many periods have elapsed. That would be 24 months. And I get the same number. Okay. So we have a couple ways to do it. The spreadsheet way is nice. You know, just take the number above, add it to the number above, times your interest rate. No problem. That's just simple interest reapplied. If we apply simple interest over and over again, then we get this crazy exponential formula, which is still nice. It works great. Okay. Sometimes it's nice to have all the monthly detail, but it's also nice to jump to any month in the future to make a prediction. Okay. So they both have their pros and their cons. So they're good. All right, so just outline this in general. So the formula we just came up with can be applied to basically any amount of compoundings per year, because there are some investments you make, you get paid back quarterly, right? So every fall, winter, spring, summer, you get paid instead of every month. There's some where you get weekly money. It's possible they can pay you out daily, or maybe they only pay once a year. All different possibilities for what N could be, how many times a year you get money back. Interest rates are all over the place. Right? If you buy a car right now, you might get like 2 or 3% if you got good credit. If your credit's not so good, it might be 5, 6, 10%. Credit cards seem to go these days from like 4% to 25%. So rates could be all over the place. But the bottom line is the math works the same whether we're talking about a credit card, that's still compound interest, but in reverse. Saving money, all the same. All right, new page. So this is what's called the compound interest formula. And it is just a growth model applied to collecting interest. And so usually we say there's F, a future value for your money. And to calculate the future value, you take P, your present value. I'll define all these in a minute. We'll just put the formula down for now. And I multiply by parentheses 1. Now, usually it's 1 plus the rate, but we might be breaking that rate up over a bunch of times during the year. Like I could divide by 12 for monthly or 4 for quarterly. And then I have to figure out how many total periods went by. So to do that, if we were doing quarterly, it would be 4 times the number of years. Monthly would be 12 times the number of years. So the exponent would be n times t. And I'll redefine what each of these letters means. So F is our future value of the money. There we go, color. And P is the present value. Sometimes you'll see a B for beginning balance. That's common too. R is our annual percentage rate, APR. N are the number of compounding periods per year. And T would be the number of years. And so it's just a matter of, given the information, plugging stuff in, and then you could either whip out a spreadsheet or whip out a calculator to figure out what's going from there. Now notice the only connection between this crazy parentheses right there and the initial balance is a multiplication. So what that means is by just changing the multiplication to a division, we could reverse and say, I want $20,000 in the future. What would I have to invest now at a given interest rate to make that happen? So not only can we start with a present value and look into the future, we could look at a future number and project back at where it would have had to start from, which is kind of cool. Okay. So just a quick look at what that would look like. The bottom line is I can calculate R over N and I can add it to 1, and then I can find what happens when I make that power. So this number I've circled here, it's just a number. Maybe it's going to be 1.1, maybe it's going to be something more complicated, but it's just a number. How do we get rid of a multiplication by a number? What's the opposite of multiplication? Division, yeah. So it turns out if you wanted to take the compound interest backwards and find the present value, you would just take the future value and divide by that crazy parentheses. The crazy parentheses was 1 plus R over N in the parenthesis to the power NT. And that just takes us back in time. So we can use this formula to move forward in time. We can use it to move back in time. And most financial formulas work that way. With just a little division, sometimes maybe a subtraction, you can go back in time instead of forward in time. And we'll look at more of that next week. So this, again, calculates present value based on some future value. Okay. So we're going to do 2 things now. First thing we're going to do is we're going to double check the amount of money I said we'd have after 24 months. And then we're going to do another, that's a present to future calculation. Then we'll try a future to present calculation. So I was kind of curious, 1, typing this into a calculator can be a chore, so we need to practice that. And then 2, It's going to take me after 24 months, I'll get about $270 in interest. I was kind of curious, how long will it take for my money to double? So if I start with 1,000, how many months have to go by before I'll end up with 2,000 in the bank? That'd be nice to know. So we'll try to answer that question too. So what I need you to do, let's go back a page or two. So this is our formula right here for the current problem we have. Our B is $1,000. Oops. And our months, 24. So just double check for me. What happens when you make this calculation on your calculator, starting at $1,000 for 24 months? Do you end up with about $1,270? So if you haven't already done it, check that number for me. Because we want to make sure everybody can make these numbers work out. Our calculators or a spreadsheet are our best friends in this course. And if you're not getting it to work out, let me know and I can help troubleshoot. Do you get it? Okay, working on it. You got it on the spreadsheet? Yeah, okay. Yeah, so we'll have a little bit of time to hit the lab to do spreadsheet stuff today. I only have a couple more problems I want to go over. Any luck? 1,269-ish. So is that the one you can just type everything in one shot, or do you have to do it in parts? You can do it in parts, okay. Yeah, so you just have to be careful there. So I would do, let's see, I guess we would have to do the 1.1 to the power first. Nope. That button right there means power. And then 24. Enter, and then times 1,000. Something went wrong. Let me give it a try. Clear. Oh, 1.01. Huh. I can't read what I wrote on the board. That looks more like it. Yep. All right, let's see if we can do it in one shot. Will it let us go 1,000 times 1.01 raised? Oh, we can do it in one shot. Yep. Yeah, so some of these problems, you just be able to type them out. So we'll keep practicing that. All right, so next thing I want to do is I want to figure out when my money is going to double in this scenario. So let's just iterate what we have. We have a starting balance of $1,000, and we have an APR of 12% compounded monthly. So we want to know, when are we going to double our money? So I'm just going to rewrite everything in the future value. So let's see. I want to know, when will I double my money? So let's see. That means my future value is going to have to be what?
2,000.
2,000, yep. So I want to know 2,000 when it's equal to my formula, which is present value 1,000 times parentheses 1 plus the interest rate, 12%, divided by n equals 12. Now here's the catch. I don't know how long it's going to take, right? So I do know I'm compounding every 12 months, but I don't know how many years it is. So I have to write T for the years in our formula. So I can't plug this into my calculator yet. I got to write it down on paper and try and sketch some things out. Okay, what things do I have control over? Well, I can clean up what's inside the parentheses. Right? What did this clean up to be? Well, we took 0.12 divided by 12. That gave us 0.01. So we know the inside of the parentheses simplifies down to 1.01. It's stuck to the power 12 times however many years go by. There's still 1,000 out front, and I still have 2,000 on the other side. And then keep in mind, what am I trying to solve for here? What's that?
Exponent.
Yeah, when am I going to double my money? This exponent, how many years it's going to take. So I'm trying to get the t all by itself. Yeah, so yeah, order of operations. If I knew the t, I would multiply by 12, then use that as the power, then multiply by 1,000. When you're solving an equation, you reverse the order of operations. So that means I have to get rid of the 1,000 first. So dividing by 1,000, I get that on the left. And now the right side's a little simpler. 1,000 into 2,000, that's not bad, that's just 2. So 2 equals 1.01 to the 12t. All right, let's see. And we developed a procedure in the last class about using an idea called logarithms. And logarithms allow us to isolate the exponents, okay? So so just to remind you what that means with an example from last class, we know that 10 to the second power is 100, right? A logarithm means the same thing as an exponent. So what I can say is that 2, my exponent, is a logarithm. The exponent is a logarithm. That's just a fact. That's the way it's defined. Okay. Like an exponent has to have a base, a logarithm has to have the base. And it's got to be the same base you started with. So I put a little tiny 10 by the g, and then I put a parentheses right there. What has to go in the parentheses? What haven't I accounted for yet? The 100 has to go here. Yeah. So that's our model for how logarithms work. And the calculator has a logarithm button, which means it'll allow us to solve for an exponent. So now what we have to do is we have to take the equation we have and see if we can apply this same system. So I'm going to rewrite our equation underneath. Backwards though, we have 1.01 to the power 12 times t is equal to 2. So just like above, I have base to a power equals some number. And the power of logarithms is to say, okay, the exponent means the same thing as a logarithm. So what's my exponent here?
12t.
12t is my whole exponent. Yep, so now I get to isolate the 12t, and the exponent has to be equal to a logarithm. And the base of the logarithm has to be 1.01 because that was the base of the problem above. Okay, and then I put a parentheses, and the only number I haven't accounted for yet is the 2, so it has to go inside the parentheses. Yeah, calculator doesn't have a 0.01, so then I can split this into 2 logarithms. And so the trick there is to just say, okay, calculator does have a log button, but I can't just let the 0.01 vanish. That changes the problem. So I compensate by dividing by the log of the old base. And near the end of this chapter, they go over this rule, plus a whole bunch of other rules I skipped, because I don't think they're as important. The only 2 rules we need are this rule up here, which changes an exponent to a logarithm, and this rule down here, which allows us to use the calculator. So we're almost done. We'll have to calculate that number on our calculator. And then the other thing we have to deal with is we don't have t equals, we have 12t equals. How are we going to get rid of that 12? Yeah, whatever answer we get from this, we'll just divide it by 12. So whip out your calculator, see if you can get your log button to work. Some calculators, it's easier than others. So give it a try, and I will come over and take a look. On Google, it's in a spreadsheet, it's actually really easy. You just type what you see, right? So for example, I could come up to my Google calculator here, and I could just type log of 2 divide by log of 1.01. That'll give me that answer, and then I could just divide that answer by 12. calculators, it's a little trickier. So we have to test each person's calculator out. I believe the spreadsheet works the same way. Let me test the spreadsheet. I think I should just be able to type equals log. Yep. Ooh. Ooh. Oh, it's not. Oh, no, it'll still work. Yep. What am I taking a log of? 2 divide by log of 1.01. And I should get that same number Google said before, 69.6-ish. Double check. 69.6-ish. Okay, so let's go around and take a look at people's calculators. If you're going to use it, you got it down on the spreadsheet. Did you get it to come out here? No. Okay. Oh yeah, you got it. 69.66. Beautiful. You got it. How did yours work? Log of 2. Okay, then close parentheses divide. Log. Okay, totally. All right. Did you try yours? It worked fine too. Okay. So there is one problem. I mentioned earlier in most books when you see log without a base, it's assumed to be base 10. That's not true everywhere. Notice on the spreadsheet when I typed, sorry, microphone, there we go. When I typed log, it said there's a log and then there's a log base 10. Then what the hell is that? Okay, so for example, if that was base 10 and I typed log of 100, it should give me the answer 2. Oh, okay, it's the same thing. Interesting. So Google Sheets apparently has 2 different formulas that do the same thing, log and log 10. It turns out I can do them with either one, so I should be able to do the same thing here. If I grab that one and put the 2 and then divide by that same one, log 10 of, what was it, 1.01, I should still get the same answer. Yeah. It turns out, this is the other cool thing. When I do the switcheroo here, I need another color. Oh, wrong button. This blew my mind when I first learned it a long time ago. As long as these are the same kind of log, it doesn't matter whether it's base 10 or base 5 or base 8 or base pi. As long as they're the same one here and here, it works. So it doesn't matter what kind of log your calculator can do, this switch works, which is kind of crazy. Because some of your calculators they have a button called LN. That's called natural log, which is log base E. E is about 2.7. It's a weird number like pi. So it wouldn't matter if we used the natural log or the base 10 log. This will still work, which is like, wow, really? Why would that still work? But it does. That's a whole nother discussion. Take Math 111 if you want to learn about that. We got better things to do. All right. So we did it. We've done a lot of stuff. We've learned how to use the compound interest formula, which is just another growth model. We've practiced logs again and taking things backwards, which is pretty darn hard. So I think what we should do next is practice a logistic growth problem, and then I want to talk about the written assignment for this week. Has anyone read about the written assignment? Oh, you haven't even looked that far? Oh man, you could have been thinking about it all week and had some really good ideas. Okay, let's take a look at the written assignment. So let's look at the written assignment first, then we'll come back to it after we do a logistic growth problem. Growth models, written assignment. And let's blow that up a little bit. All right, so the written assignment is for you to do some internet research and find something that changes over time. And that somebody has recorded this change over time so that you can graph it and see if you can make a model for it. Like if something's changing over time, it could be growing linearly, kind of straight, or it could be growing exponentially, or maybe something else. So let's brainstorm for a minute. Think of some things that could change over time that we might record as human beings. Global temperature, that's a great one. Yeah, you could, out there somewhere, you're going to find websites that have average global temperature from last year and the year before and the year before and the year before, and you could see, do they line up? Are they going up? Are they going down? Are they curved? It's curved, okay. What else could we look at? Population growth, yeah. Well, what's the population in Pendleton over the last 10 years or over the last 100 years? What's the population of the US? What's the population of the world? Yeah, they're all curved too. What else could we look at that might change over time? Interest rates, yeah, the federal interest rate, which everyone else bases their interest rates on, yeah, they change all the time, right? They were zero for a while we were in the recession. I think they finally started bumping them up maybe a little bit. So that's something we could look up. Oh, this I thought of earlier. I was thinking of global warming, but I didn't want to do that. I want to do something different. I was like, well, it's claimed, and there's a lot of proof scientifically that we are the cause of some global warming now, right? And what's part of that cause? Well, automobiles take a lot of hit for that. They produce an awful lot of greenhouse gases. So I was thinking, well, how many automobiles have we had in the world over time? And I looked that one up, and I found some data on that one. This is pretty cool. Automobiles. And I found data 1960, 1970, 1980, right up through 2012. Let's reduce this down. And then I graphed it. So here is my graph of the car data. Is that straight or curved or a little of both? And then it starts to turn here. Yeah. So I was thinking it would be more like people data, which starts out kind of flattish and then curves up. Like, for example, I looked up US population. Where's that one? US population. And oh, here's my graph. Let's shrink this down a touch. Okay, so the blue graph is the US population. The red graph is me trying to model it using the techniques in this chapter. So let's see. Let me regraph it. And Google Sheets does a good job of graphing. So does Microsoft Excel. You just give it a table of numbers, highlight the table of numbers, and then say, please give me a graph. And it will say, would you like that graph as a line? Say, sure, that's a nice graph. Or I could go to chart types and scroll down and say, nah, I want a set of points instead. It's up to you. Okay. So here, the population started off kind of slow, but then all of a sudden it starts to take off. And this segment here looks almost straight, but this is definitely curved near the bottom, right? If I zoom in on that, it'll look curvier. I started in, I believe, 1790. Yeah, 17. I think that's when we started doing the US Census. So this is data from the US Census Bureau I grabbed online. And so let's see, did I write? Actually, no, I got this from Wikipedia. And one important thing is you got to cite your source. I forgot to cite my source on this one. I'm bad. But I bet I can find it pretty quick. US population. Oh, this was cool. Check out this Google graph. As I move my mouse, it shows me what the numbers are on the side. Isn't that wicked cool? They just started doing that a year or two ago with certain things you search for. If there's data, they find it, and then they graph it for you, and it changes. Even better, it gets even better. Check this out. They also have related statistics in the bottom right there, so that when I move this, it shows me related things, like GDP, gross domestic product per person. So I was curious about that, so I went and clicked on that graph. And that's got a little bit of a curve to it, doesn't it? And so then I got to ask myself, and it's got that little hump there. Interesting. Ooh, what's that hump? Yeah, this is when we had our recent recession in there, 2008-ish, 2010. Notice there was a little delay in the gross domestic product, right? So banks failed, all hell broke loose, And so it took a year or two for the whole country to really feel it. And then it took us a while to start climbing out of it. So that's interesting. So your job is to find some data and then see if you can do something with it. Now, what types of change have we been dealing with? Well, we've been dealing with two types. We've been dealing with linear change. Oops, highlighter, which is straight, yeah. Oops, I made it go away. So linear is straight. And then we have exponential, or geometric. And it usually has a curve kind of like that. And the usual thing is it gets steep out on the end. Okay. Sometimes they call it like a hockey stick kind of shape to the graph. There are exponential curves that go down. So there can be different variations on them. So there's another kind of exponential that, let's see, goes like this. And it kind of hits a ceiling. There's another kind that's the reverse of this that heads down and hits a floor. So an example of hitting a floor, anybody ever drink a hot drink like coffee, tea, or cocoa? Right? If you let that sit in a room, what's going to happen over time? It's going to decrease down to whatever the room temperature is. Yeah, so that's that's called an exponential cooling equation. Right? So that's what this could be, like coffee cup temperature. Oops, coffee cup. This one right here could be like a cake in the oven. The oven's at some temperature, and if you throw something in the oven, it's not going to be as hot as the oven at first, but it's going to start warming up. The hottest it can get is the oven temperature. Usually we pull the cake out before it gets to the oven temperature because otherwise it would be burnt. But yeah, so that is the logistic growth, and that's a combination. And so it's not strictly exponential, but it's got characteristics of this kind of exponential growth mixed with that kind of exponential growth. And the equation is a bit more complicated. So each of these graphs I have drawn here all come from A times B to the X. But the logistic one is much more complicated. It starts off like regular exponential, like that. But then all of a sudden, it has a reason to change direction and do that and have a ceiling. So a logistic curve is an S-shaped curve. It's related to exponential growth, but it's a bit more complicated. I think usually a logistic equation looks like 1 over A plus B times C to the X, if I remember right. Okay, so it's a wee bit more complicated than just a number times a number to X. And like the compound interest formula, our C in the compound interest formula was kind of complicated because it was 1 plus a fraction. So usually logistic has that stuff floating around here, 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 or up with the X. So they're a bit beastier. And modeling logistic equations is a heck of a lot harder because you have a whole bit. Sometimes there's another number up here too. Sometimes there's another number by the X. So the nice thing about linear and exponential, for exponential, all I have to do is figure out two different numbers to get an approximation of what's happening. With linear, it's mx plus b. So again, I just have to come up with two different numbers. Okay. So I just wanted to show you how I might come up with those two different numbers based on some of the data I found online to give you some tips on how to proceed. Okay, so if you find data that's logistic, that's awesome that you found it, but it's not going to work for this project because coming up with a logistic equation is a beast, and we haven't gone over that. We do have the tools, though, to come up with either a linear equation or a basic exponential equation. We can pull that off. So we're going to try that right now. So I'm going to give you some examples. I wanted to look up some other stuff I had. Let's see. Oh, another thing I was thinking about is more and more people have smartphones, right? So I was like, has anyone kept track of how many smartphones are in the world? And so I looked up some data, and that was sketchier. Like for last year, some websites said there were like 1.6 billion cell phones in the world, and other websites said there were 2.6 billion. Right, a difference of 1 billion. That's a big difference. So these numbers didn't make me happy when I found them because they weren't as easily comparable. But I did found one site that had data on the U.S. that looked pretty reasonable. Okay, so this was the number of smartphone users, not number of smartphones, number of smartphone users, because some people have more than one. Do you know anybody with more than one smartphone? I know a lot of people. I got a friend of mine who's got 3. I don't know how he does that, but like a lot of people in business, they'll have a personal one, they'll have a business one. Some companies say, hey, you got to have a business cell phone. Check out this data. Does it look linear or exponential? Or yeah, it could be like one of those upside down exponential ones. Yeah, and we can figure those out. They're a little harder. But it kind of looks like a half a parabola or half a circle. So if you look at if you find some numbers and then you graph them and you're like, oh, I don't know, you can always just find a different example. So after looking at this one a little while, I'm like, it might be an upside down exponential. I'm not sure. So I think maybe I'm just going to pick a different problem. So you might decide I'm not going to do it. I could make a different kind of graph on this one. So if I highlight the numbers, other thing, a lot of websites will give future predictions. Like here, they have, blow it up, sorry. They have, the stars mean it hasn't happened yet. So this study was done in 2014. So they were predicting how many cell phone users there were going to be in 2015, 16, 17, 18, 19, and 20. So I did check some other sources, and I found numbers between 180 million cell phone users and 220 million were the numbers I found. And again, think about, well, how does somebody count that? They certainly didn't visit every person in the United States and say, show me your cell phone, or show me all of your cell phones, right? So collecting data has its challenges. But if I graph this data, maybe I could graph as points and it might look clearer to us. That's an interesting shape. But notice it starts to come down here, according to their model. If it's an exponential, it can't come down. Yeah. So if that point was accurate, I'd say, no, it's not exponential. Exponentials keep rising. They might hit a ceiling, but they're rising toward the ceiling. Or they're rising forever out of control if they're the regular exponential. Okay, so this is one I would say, nah, it's cool data, but I can't do it with the tools I have here. I could go for the US population. So let me show you what I did on this one. I'm going to copy some of this data over to another sheet. So these populations came from the US Census Bureau. I found them on Wikipedia. Okay, so eventually I would have to, at the bottom, put the website of where I found it. I'll come back to that later. The next thing I did is say, okay, if the graph leads me to believe it's exponential or even linear, I have to either find the slope or the growth rate. Those are the things we need. And then I need a starting value. So whether it's exponential or whether it's linear, I need a growth rate, a slope, and a starting value. So first thing you got to do is graph the data. And usually when you find the data, it will probably be graphed for you. You can do a line graph for it. or you could do a dot graph, whichever you prefer. I don't know which one I like better. I'm going with the dot graph. So I'm going to put it in there. So what do you think? For this data, am I better off going linear or exponential? It's got a curve to it, so yeah, so linear is out, so we'd have to go exponential. Okay, so if it's exponential, that means I'm trying to find a starting value, and B, a growth multiplier. Okay, so let's write that down. So exponential data means I need something like A times B to the X. A is some starting value. Right. And so if I think about the starting value for a minute, the data I was given started in 1970 and then 1790. I messed up those digits. (1790) and then went to 1800. The census happens every 10 years, so that's why there's 10-year intervals. So the next one would have been 1810. So although this is the year, I could make another column I'm going to call T and say 1970 is my 0 year. Then 1800 would be what?
1 year.
10 years later in this case. Yeah, I would go for 10 years later. And then 1810 would be 20 years later and so on. Okay. Because otherwise, then this gets more complicated, the X up top, if we try to go with 1970 as our starting year. So we just say 1970 is year 0. And then we have to interpret what the number means from there. And then we have our population. As far as B is the growth multiplier. And we must remember that the multiplier is always 1 plus the rate. So sometimes the place you get the data, they might say, hey, we think the growth rate is 2%. Or they might say the growth multiplier is 1.2%, something like that. So we need to try and figure out that. The way multipliers work is if you multiply over and over to get the new number, to figure out what the multiplier is, you have to do a division to go back and figure it out. So the way we do it with exponential stuff is we just make a new column where we do division, and we see what happens if we take the current value and divide by the previous number. Right? Because remember, an exponential model is a recursive model. How do we come up with the new population? We multiply over and over again. So to go backwards, we have to divide. So this says that the growth multiplier is what I'm finding here, is about 1.33 to get from 1790 to 1800. So what's the growth rate then, if that's the growth multiplier?
Zero point 0.33.
Yeah, it'd be 0.330, so about 33%. So what we could say is over that 10-year span, the US population is about 33% greater than it used to be. Okay? The 1 represents the starting population. And then I just repeat that. So in the next cell, I just try the same formula. So I can really just fold that down and see what do these look like. So from 1880 to 1810, it looks like the country grew over that 10-year period at about 38%. And then at about 33% over the next 10-year period. Another 33%, 32%, 35%, 35%, 22%. Ooh, what was going on in that 10-year period? Civil War. Yeah, so we lost a lot of people in the Civil War. That was nasty. We're very lucky we weren't alive then. All right, so I can keep going that down and see if that's relatively consistent. So we can see that in the 1800s, we grew roughly in the 30s, around 30%. And then after that, we started to drop into the 20s, growing, and then in the teens. Ooh, in the 1940s, what happened there? World War II, yeah, okay. During a war, people don't have time to procreate, and a lot more people die, right? But then we shot up again, 1960s. So in the last, like, 50 years or so, our growth rate has been around in the 10% area. Okay, so if it's definitely exponential, then I should find that these percentages are all the same, but they're not. Okay, so I have two choices here. I can either throw this out and say nope, not exponential, or I can say close enough. Let's find an average. Okay, so I could go for an average. Other thing to consider: this 33% is over how many years?
1 year, 10 years.
Over 10 years, right? So really, I have to think about this simple interest idea. I have to take that 33%, so that's 1 minus this cell, and I have to share it over 10 years. Oops, I did the subtraction in the wrong order. This minus 1. And so if I take that number and divide it by 10, then I get a yearly rate of about 3%. Okay, that makes sense? Like the way we did interest before, if you get 12% for the year, you should only get about 1% per month. Okay, so it kind of works that way here too. So what I'm going to do is I'm just going to say, okay, let's just average those growth multipliers and see what we get. So I'm just going to ask the computer to average. And chances are most data sets don't have this many numbers, so yours will be a little smaller and easier to deal with, most likely. So on average, over that time, it looks like we were growing at about 22%. So I need to get the rate out of that, so I'm going to take 1 away from it. And then I need to balance it over 10 years, because those are all 10-year numbers. Okay, so this says I should use a growth rate of about 2%. Okay, so what I'm going to do next is I'm going to try and actually mimic this graph over here with a model. Okay, so I'm going to insert a column here to do that. Actually, no, I'll just go to another table. That's cleaner. Okay, so what do we think our yearly growth rate is? About what? About 2%. So we're guessing based on the data that our yearly growth rate is about 2%. So we're going to use that here. So if that's our growth rate, what's our growth multiplier? That'd be 1.2. So I just take that sucker over there and I add 1. That's our multiplier. And so what I want to do is make a formula for that. So what I'm starting in 1970, right? Mm-hmm. Or 1790. It's the like second or third time I did that. So that's my A, and I want to multiply by my growth multiplier raised to the power. Now my power has to be years after 1790. Oh, I get it right that time. Okay. How do I calculate years after 1790? Like how many years is 2016? How many years is that after 1790? How do I calculate that? I just subtract, right? But the subtraction has to go in parentheses. So then I just subtract the current year from 1790. So that's the trick. I could have either made an extra column for that, like I did in my document over here, or I could do it at the same time in the formula. Pros and cons to each way. All right, so I think I got my formula. I'll do it the other way just to double check. And then I should just be able to fill that down, and hopefully my numbers won't be too far off. Oops, oh man, I messed something up. 0. Oh, I know what I messed up, I think. Oh yeah, when you fill down a formula, it moves the cell references with you. Does anybody remember how to tell it to freeze a row? You put a $sign in front of what you want to freeze. So double clicking here, my growth multiplier needs to be frozen in row 2. So I put a $sign in front of the 2. Let's see, is the starting population always the same? Yeah, I'm always starting at the same. That's my A right here. Okay, so I need to freeze that to, Okay, I think I'm okay now. The only thing that should be changing is the year. Yeah, okay. And what happens when I make these spreadsheet models, I almost always screw it up first 2 times, and then I say, okay, what did I forget to freeze? And then I try it again until it looks like I got it right. All right. So let's throw some commas in these numbers so they're more readable to see if they're actually, we can just graph them, right? So this is my prediction. And Google, make me a chart. That's not too bad. I start out okay here with my red line, and then I kind of lose it here. Why did I lose it there? I was guessing at a growth rate of 2%. What was it really in the 1800s? It was more like 3%. Yeah, so my model's growing slower at first, and then faster later. Notice how my red model's steeper over here than the blue one? Because 2% was more like what was happening in the 1940s. In the 2000s, we're growing more at like less than 1%. So it wasn't possible for me to find a perfect exponential model, but I'm close in the beginning, I'm close at the end. It's got the kind of right general shape. And so that's what I'm looking for. Could I use this model to predict far in the future? No, because if you look, the red line's looking pretty darn steep. It's heading up, and the blue line's starting to slow down a little bit. So I can't go very far in the future, but I might be able to predict what's going on in like 2021. Not too far off, right? So once you come up with a model, I want you to then use your model to say, okay, let's go 1 year later or 10 years later, depending on how comfortable you are with your model. Okay. Let's do this one more time for a different one. And I'll share this with you guys too, so you have it to take a look at. So let's see. We can insert that. And let's label these better. So this is US population. And I was playing around with all kinds of different calculations here. This one here was US population with a guess at the rates. And this one here was US population, oops, oh, I typed in the wrong spot. Undo. US population with a model. So that might help when you're working on yours. Share, advanced, public. And so I will share this. Let's see, I can reply to this right here. And I can throw in Aries US population playground. Hyperlink that to that spreadsheet. Yeah, so when you go to the growth models, you'll see underneath the thing, there should be my sample here. All right, so let's give you another example, and then I'm gonna shut up. Other example was automobiles. Yeah. So with the automobiles here, you could argue either way that, hey, this looked like it might be heading exponential at the end, or you could just say, most of it's straight, it's linear. So let's go with the linear model on this one to take a look at how we would calculate a linear model. So somewhere on the internet, we found some data. This one I remembered to cite my source, so I was good there. If it's linear, that means I'm trying to find a model y equals m times x plus b. So what does m represent?
Slope.
Slope, right? So to find slope, instead of dividing consecutive y values, I subtract them. Because slope, you have to do a subtraction. So I'm just going to go over here in my spreadsheet, and I'm going to take the new number minus the old number. Another thing to notice, let's see, 60 to 70, 70 to 80, 80 to 90, 90 to 2000. At least the first few jump by the same amount. That's important. So I'm just going to scroll this down for the first few right to there. Because then it gets weird. 2005, 2009, 2010, 2012. the heck? Okay. All right, so let's see. And then next we would need to divide those by 10. Divide by, oops, number divided by 10. And let's put commas in there so they're more presentable. Get rid of some decimals. That doesn't, oh yeah, that worked. So this says from 1960 to 1970, there was an increase of 11 million automobiles. No, oh, I'm sorry. It was 100 million automobile, almost 120 automobile increase. So every year we were roughly increasing by 11 million new automobiles per year in the US. From the span 70 to 80, we were increasing by about 16 new automobiles per year. Now here, an automobile could also be a truck or a light truck. So anything we drive on the road is what they're counting here. So it's not just cars. About 17 million, about 16 million. So there's a couple of ways we could proceed. We could go and kind of average these to get a slope. Another thing we could do is you could just pick 2 points like this one and maybe this one and use those 2 points as the one you're going to find the line through. So let's see, what's that? 1960 and maybe, what was that one? 2009 maybe? Yeah, so maybe I'll grab 1960 and 2009. So let's do this together, see what we get. So I'm going to highlight 1960 and 2009. So we're going to use those two numbers to come up with a line. And then we'll test that line. So let's copy those into a new sheet. Oh, it didn't copy them. Only got one of them. Oh, it really messed that up. Oh, it didn't get the first one. I'm sorry. I can't read. 6s and 9s look the same, don't they? No? Let's flip one. Okay, so there's my two numbers right there. Let's blow them up again. So we need to find the slope. Remember, slope is rise over run. Okay, so I'll calculate the rise, you guys do the run, and then we'll finish it. So my rise is this number minus that number. Then we have to divide that by our run to get the slope. So whip out your calculators, come up with a number. Let's see, what do I get? 1960 to 1990. 852797000 divided by, was that 49 years? So divide that by 49, and that'll be our slope. So this number here is our rise. Oops, rise. So slope should be that over 49 years that elapsed in that time. Ooh, that's a big number. Commatize it. Get rid of some decimals. So it's about 17,400,000-ish is our slope. So we could round numbers a little bit just to make it easier. We could say, let's call it like 17.4 million. Would that be okay to say? 17 million, 17.4 million. That's ballpark. All right, so then we have to come up with a y-intercept, our b value for this. All right, so that we can do in a couple of different ways, looking back at the data. We could either say 1960 is our starting point. Otherwise, if we use the number 1960, then year 0, like the cross between what, BC and AD is our year 0. That doesn't make sense. There weren't any cars back then. Right, so I think maybe we should start at 1960. Okay, so that means I kind of need another column. So I'm going to sneak it in between these two. So let's insert a column to the left. Ooh, whoa, what happened there? Oh, I forgot I had all that stuff above. The original data came horizontal, which Google did not like. So I had to re-enter it vertically. Okay. So here I'm going to have to say this is like years after 1960. And so I'll just say, okay, this is equal to whatever number is here minus 1960. And so the numbers I need to work with would be 0, 10, 20, 30, 40, 45, 49, 52, 50, and 52. So those are the actual years I'm using here. And then let's move these guys over a little. Oh, not that far. Oh, now they're behind there. Okay, I didn't need them anyway. All right, so let's see. So now we're going to make a prediction. So what the 0 means is this number is my y-intercept. Okay, so here come my predictions. So did we calculate m? Yeah, that's the roughly 17 million, right? Okay, so for my prediction, I go equals my slope. Let's call it 17.4 million. So 1, 2, 1, 2, 3 times the years after 1960 plus my y-intercept, which is going to be the 1960 number of 126,888,000. Now, the cool thing about picking 1960 as my starting value, that means my prediction for 1960 is always going to be right. Okay. After that, I have a different slope, and so things are going to get interesting. All right. And so now I just want to graph these two next to each other and see what happens. So I'm going to graph these 3 columns. So I just click, give me a graph, Google. And let's shrink it down. Chart types. You could always graph it by hand. I wouldn't recommend that, but you can. Ooh, so the blue one is the data I found. The red one is the one I made up. That's not bad. You know, because of that little hook at the end that I grabbed, my data is a little high at first, and then it's a little low at the end. That's pretty cool. All right, so quick review. Let's insert that sucker. Back to the notebook. So your job, again, is to go search for some data that's either linear or exponential. The data is most likely going to change over time, probably years, could be months. If it's linear, your model is going to look like y equals mx plus b. And so you have to have a slope and a starting value. If it's exponential, it's going to be something y equals a times b to the x. And then a is your start value. And b is your growth multiplier. Slope, remember, is change in y, like y2 minus y1 over x2 minus x1, right? So that's why we had to do those 2 subtractions and divide with that last example. The growth multiplier is usually going to be something like y2 over y1, or maybe y3 over y2. If something's exponential, if you divide consecutive values, you should get the same amount each time. So remember I did consecutive divisions on that one with the US population. And for the first like 100 years, they were around 30%. That was cool. So I could just say, hey, I'm only going to predict population for the 1800s. I got good data there. Okay, so you could decide to limit the data you get. If you do, you should make a note, hey, I chose to use less data than they gave me. Here's why. So you're just going to play around, see if you can find something. If you need any help, then post a note to the forum and the rest of us can start giving you ideas about what to look up. But I started with ideas by just going to the news and see if anywhere in the news they had a cute graph that I might be able to use. Like, oh, here was another one I found. Where is it? I think growth models, weighted example, online data. Yeah. So Twitter went public a while ago, and apparently they have not been. They've been losing money, not making money since then. And these kind of lined up. Unfortunately, the more I read the article, the less I understood what the graph really meant. And I looked up some other data about Twitter, and I couldn't get the numbers to match. So either the people at the New York Times who published this didn't publish all of the information, or they didn't give an accurate description of what this really means. So I decided maybe I won't use it. So if you come to some data that you say, oh, this looks cool, but then you read about it and you're like, I don't get it. Find something else, okay? And that happens a lot. You guys read stuff regularly you don't get? I do. So, yeah. So it's bugging me that I don't understand this graph, but it seemed pretty straightforward. But then when I looked up Twitter's financial statements, I couldn't get the financial statements to match this. So apparently I need to go talk to an economist who gets it better than I do. So anyway, do some looking out there for things that change. Sure things, usually population changes exponentially. So if you look up population in different places over time, you're likely to find exponential data. Linear, you never know. I found lots of crazy graphs out there. Let's see. This one was cool, but I couldn't figure out how to use it. It kind of lines up, but it's not over time. This is a graph of gross domestic product per person. So how much money the whole country makes divided by each person versus people that reported owning a smartphone. So if it's a rich country, more people have smartphones. It's a poor country, less people have smartphones, was mostly what they were getting at with this report. So sometimes you might find data that just doesn't fit because our data needs to change over time, and they're not showing me time here. So although it looked like, ooh, I might be able to use this, they even give the line, wrong kind of data. So if you have any doubts, just send me an email. Say, hey, I found this. Do you think I can really use it? And I'll write back and say yes or no, if I think it's good or not. And if you need more time, like this is due Saturday, if you don't think you can get it done tomorrow, apply late pass. Come ask me questions about it Monday. All right? So don't sweat it. Have fun, do good math. I went over time, sorry. I thought we'd have time to play. I get too excited about all the data.
So, Mr. Parker, do we
Yes.
search one data or two data?
Just one data set, and the data set needs to change over time. So like here with the Twitter data, here I have it changing every quarter. So this would work, provided we understood what the y-axis meant. And if you want to look it up, I have the website here. You could go check it out. I can share this one too.
Okay.
This one wouldn't work. What else? Oh, I found some other data about, let's see. Oh, this one was kind of cool. So somebody could look this up. I'll share this one too with everybody. This one had data about cell phones, computers, MP3s, game consoles, tablets from 2010 to 2015. So there might be something there to take a look at. That was cool. Tablet ownership's on the rise, might be linear. There's the auto data. And the only catch is, and this one's going to be hard to tell, is you're not supposed to do the same thing somebody else does, but you're not going to know until you post it, so don't worry about that catch. But I'll share this one with everyone to look at too for ideas. So I got these by just, it took me, this was like an hour's research, and these are half the things I came up with. So you'll find something out there. So as far as to data, it'll be time versus something else, like people, money, cars, cell phones, global warming temperatures, whatever you decide to do. So it has to have two columns, time and then whatever we're measuring over time. All right. Have a good day, everybody. Have a good weekend.
Okay. Have a great day. Bye.
Thank you. Bye-bye.